This episode was brought to you by Pentester Academy, the leader in online cybersecurity education. Join over 10,000 professionals from 90 countries to learn security online. I'm Marley Oxenome, and I'm here at the Riscure North America headquarters, and I'm sitting here with Edgar Mateos, who is the lab manager, and he's going to show us a live demo right now. Thank you so much for doing this. Okay, so tell me exactly what this demo is, and then just walk me through it.
Well, we're going to have a demo on side channel analysis. This is a board that we call it Piñata. It's a board that is we use for analyzing some techniques and study some of the tools that we are developing. Mm-hmm. And in this case, what we have is a scan. We have an electromagnetic probe scanning the chip. We are recording those emissions from the chip. The chip is performing encryptions on AES. Mm-hmm. So at each point that the probe is moving, we perform a full run of software AES, and then we record it on the tool. So okay. Here on the screen, we have the duration of AES, and when we are scanning, we have the emissions of the EM. And the reason we are scanning all the chip is because we want, when you are doing an EM attack on side channel, you want to figure out, you want to place your probe on the best location that you can for getting the most of the information. The crypto is going to be executing in some regions, and if you place it in a region that probably is really high intensity but is not where your crypto is, that's going to be bad. So in this case, we are executing AES, and then after that, we're going to have some ways to measure what's happening. So in this case, the chip is going around. Now, the scanning takes some time. Mainly, the most of the time is moving the probe from one point to other. That's why we prepare some previous scan, and I have a previous scan on the screen. So I'm going to stop the scanning that we are running here. Mm-hmm. So if I stop the scanning, we're going to have a trace that is going to have a number of traces at different points. Mm-hmm. And well, also always you just you need to save the acquisitions. Let's put it here, 5. So this is a screenshot that I have from before, and I'm going to show you how to spectral intensity. So we come here and we say that we want the spectral intensity of this set of traces. Oh, oops. Okay, this is the set of traces. I cannot see how many. Oh, we have 330. That was the open new set traces. Okay. So this is the right set of traces. So let me see, available. So from here, we're going to run the spectral intensity of the traces. And then this gives you like the intensity map of what was happening on the chip. Okay. So with this, you can click on the trace that you want, and you can look at how the trace looks like. Or you can click on a different location, on a different point, and you can see what's happening. So the main idea here is that you are going to focus on some areas. So for example, here looks interesting. You can say, well, this the amplitude and the features that we have on the trace are clear. So you can say, well, I want to do my acquisition in this area because I have a number of points that have a higher intensity. Mm-hmm. So you just move the probe to that location. So you just say to the probe, move to that location, and move into the power analysis. Now, when you are doing that, once you get into the location, you get lots of traces. Lots of traces could mean you never know beforehand how many traces you will require. You never know if it's going to be better EM or if it's going to be better power. So at the end, sometimes if you have the opportunity, you have to try both. You have to try EM or you have to try power. Power, it's a little bit more invasive because you have to cut the power planes in order to get access. EM is more like, okay, you just have an antenna on top of it, and you don't have to modify almost anything on the setup. Now, we have already done this experiment, and with EM, you need more traces from this setup than with current. So I'm going to just make an acquisition of the chip using power. So in this case, well, when you are acquiring the trace, one of the things that you always want to figure out is that you have the trigger. The trigger is going to be the range when your encryption is going to be occurring. It's going to be the framework where you're going to be working. So in this case, we have this. We're saying that is the element that we have. We're going to have random data, and we say the run. So once we run this setup, well, in this case, it's getting the trace for the EM. I need to make a small change to get the power. Sorry.
No, it's fine. Go ahead.
This is how the power looks like, how the AES it looks. Now, for those of you who knows AES, and they are familiar with AES, AES has 10 rounds. So in this profile, we can see something about blocks of 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can see like about 10 blocks when things are going to be happening. And that corresponds, or that should looks like the runs of AES. Now, for running in this case, what you need to do, well, this is what we have for the trace, and we have what is our trigger. So usually you can have both. You can have the power and the trigger. Let me set settings local. Okay. So you can see how your trace looks like and how your trigger and your trace, and from here, well, you can proceed. Now, when you're going to do an acquisition, what you want is you want to get only the traces. You don't want to get the trigger in the middle. So for that, something you can do is you can say, well, give me 5,000 traces. And you just ask the tool to do it. Now the tool is going to go, it's going to be capturing the data, it's going to be running. Here we can see that we have now 90. So it's relatively fast, but the thing is, if you need to go, you never know beforehand how many you will need. You don't know if you need 1,000, you don't know if you need 100,000, you don't know if you need 10 million. So it's something that you have to be building on top of that. So we're acquiring here, and in the background I have another trace that I have already acquired before. And this trace, well, it's very similar than the ones that we have. So that's the type of things that we could get after a few minutes on the setup running. So in this case, we have 7,000 traces. Now, once you have the traces, if you look with care on the trace, you are going to see that these traces are not necessarily aligned. They are not perfectly aligned one with each other. So on side channel analysis, one of the first stages is to align the traces, so that that's going to improve the quality of your results and the speed up the analysis. So in this case, what I'm going to do is I'm going to align the traces at the beginning of this part. So I'm going to say here we have a model in our tool, that is inspector that we're running, that aligns the traces. So we're going to say use that segment, and it's going to align the traces that we have. So in the background, the model, it's running the alignment, it's getting those values, and it's telling me at some point, it tells you, the tool, what's the correlation between the traces. So you can fix what's going to be the tool is going to try to match the traces with the maximum correlation. So when the traces are the most similar, so that's what the correlation means, how similar they are. Okay. So, and once they found how much it has to shift each one of the traces, is going to align it at that point, and it's going to jump to the next. So we have a reference trace, we align all the traces, and then after that we're going to end with an alignment set. And in this case, we're almost there. It's 7,000 traces.
Almost, there we go.
Yeah, so now the main reason we are spending here kind of some time is that the original set of traces contains 220,000 samples. So it's a relatively large number of samples that we have. So let me save it. Let me save it here like a time and alignment. Let's put it here a value of 1 or demo, so that we know exactly what it was. Okay, let's say none, because it's going to try to save just that part, and it's going to throw everything away. So at this point, it saved everything. As I selected a section and then I put save, the tool is going to say, do you want to save just this section? And then if by anyhow I say yes, it's going to save me just that piece instead of the whole document. Now we can just double check what happened with the traces. And then if we overlap the traces, we can see that now they look better. The alignment, it looks better than before. Now, once we have this, we still having a very large number of traces. So some techniques that are used are called the compression. What we want to use, in this case, I'm going to use window resample. Window resample, what it's going to do is it's going to take 40 samples of the trace, of each one of the trace, and it's going to sum all of them, and it's going to say, okay, the average of this trace is about this amount. So it's going to give a kind of a good profile of the trace, but what it's going to do is it's going to compress the trace in about by 40 about.
Okay.
So if you look at this trace, at these two different traces, there is not much difference in the shape. Now, again, save it. But the results and the analysis are going to be kind of similar. They are going to be different because, well, we are dealing with different things. Sometimes the leakage on multiple samples adds into a single sample. So sometimes it's better to use the compression, so that you can compress all the leaks that you want into less samples. So now we have this element. Now, one of the tools on the main tools on side channel is the correlation. You want to see where is your input, where is your output, and that helps you to figure out, okay, where it's my AES. Or here it's saying that it ended acquiring the 5,000 traces that we asked. So our model that was in the background running, it runs. Let's put it demo 5,000. So let's get back to our trace that we have here. So in this trace, it's aligned, it's compressed. And what we're going to do is we're going to run an analysis that is called correlation. In this case, correlation, it's going to tell us where the data of the input it's correlated with the trace. So we're going to say the 16 traces. So the values that we have on the input are correlated in this area.
Okay.
And the values that are correlated to the output are in this area. So when we put all together, we already know that here we have the input, here we have the output. We already know it, but sometimes when you don't have an exact picture or a perfect trigger, this tool between the correlation between input and output allows you to figure out exactly what is the action happening. So this is a tool that can be. Some people can say, well, the output is smaller than the input, so you have more leakage on the input. Not necessarily, because we are aligning in the input. If we are aligning on the output, probably would happen the opposite, that we have a higher correlation on the output. Now, once we have this nice correlation trace, well, we always have to save all the steps. Usually, it's good to have all the analysis. So we have this trace set. So we already know the correlation between the input and the output. You can run different correlations. Let's say when you know the key that it was used for the encryption, you can use it for the analysis. At this point, let's run a first order analysis that is not going to make use of that. So it's going to measure the correlation between the power on the trace that we have and the data that would be at certain intermediate state at some of the in the first round in some of the states, and then we're going to try to retrieve the key. So in this case, we're going to select a region that is related with the start of the AES. So we already know that here are the inputs, that here something is starting on the first round, or because we are assuming that here is the 10 rounds, and then we're going to run the tool with that. So we have in the tool embedded some tools, in this case a module that it's called first order analysis. And the first order analysis, we have to say, okay, what samples are going to be, how many traces we are going to have. I'm going to put here, let's say the 2000. I'm going to run the analysis not with the 7000, but only with 2000 to see what's happening. We can say that we want to use correlation as the method to use. We can say that we want to compare the peaks when the correlations are the maximum. We are going to say that it's an attack from the input. We align it in the input, so it makes sense for us to attack from the input. We can say here is round one. If you change these values, okay, it's going to give you different options for round 10. And then we're going to say that it's an S-box, Hamming weight, and then we run the analysis. Now the progress here is saying 70%, 80%, ready.
Nice.
So it run the analysis, and let's say, yeah, the correct key was found. So nice. It was able to retrieve the key. So basically that would be like the time that it takes for attacking, retrieving the key once you have a daemon. So in the case of analysis where you don't know what's going on the analysis, you will need different techniques. Sometimes your system has contrameasures, and you have to do something. You have to figure out, okay, how bad it's going to be this without having to break the tool or without having to recover the key. So you just one kind of a comparison. There is something that it's called TBLA. And then in the TBLA, what you do, I'm going to run another acquisition here where we have the scope sequence. Now, in this case, what we are going to do is we're going to say that we want to run TBLA for a semi-constant, and then as we already know the key, because we recovered the key in the model that we have, or we can just select it, or we can say copy. We're going to put it here, the key, Control V. We place the key that we want, and then we can make an attack, let's say, or highlight some round. Which round would you like? Let's say round 5. We run something there, and here let's put it with a Hamming weight of 5. And let's acquire not 5,000, but probably 2,000 traces. And okay, let's go for round 9. So it's going to be easier to align at the very end, and it's going to have a better impact. So now what we are doing is we're acquiring traces. Is the same thing. It's going into the step of trying to get the traces, trying to run. Now, I have another setup where I have the traces for TBLA on the last round. Let me open it. Open trace set. TBLA round 9. We have this value. So these traces are from TBLA at the aligning at the last round. They don't have any extra compression. But then from here, what we are going to do is we're going to run the analysis that we were mentioning on the TBLA. So we are going to come here to the TBLA test. We just say what's going to be the report that we want, how many traces we have, and then the tool is going to perform the TBLA analysis on the traces. So now what we have on the trace is we have some kind of statistics. Here we have the number of traces that we are considering. We have 2,400 traces on the original set. So we have a kind of statistics, how the leakage is going to be becoming more and more relevant. There is a known academic factor of 4.5 that when you have leakage higher than 4.5, that means that if you acquire a very large number of traces, you could, or a certain number of traces, you would be able to retrieve the key. Now, you're going to say, well, you were analyzing 2,000 traces to retrieve the key. So if our system is kind of leaking the same at the beginning that at the end, it's not necessarily the same, always the same, but let's assume that that's a valid hypothesis at this point. We would say that when we were attacking the acquisition of the traces for the round 9. We would say that we have a TBLA value of 30 standard deviation. So this is kind of a reference parameter at t-score of 30 says that this system with about 2,000 traces, we would be probably likely to retrieve the key. So when you have some kind of contrameasure or something implemented in your system, sometimes you don't want to spend, if you're going to be, in our case, we were analyzing 2,000 traces, but if you are trying to analyze 100,000 or 20 million traces, and your trace set is like a few thousands of traces, that would take a very long time. compared with an analysis with a TBLA, where you would just eventually say, okay, I'm not retrieving the key, but I have evidence, or I have the certainty that if I keep acquiring traces, I'm going to get, or if I tried, I would probably retrieve the key. So this is the main thing that we have. So in our in side channel analysis, you have to keep tools at hand. You have to use whatever you have available. You have to use lots of statistics, and yeah, they're a nice topic. Thank you.
This episode was brought to you by Pentester Academy, the leader in online cybersecurity education. Join over 10,000 professionals from 90 countries to learn security online.